I would like to show you Grasp, a non-textual code editor for the Scheme programming language that I've been working on for a few years now. But before I move on to the demo, I would like to discuss the ideas that have been driving its design. My motivations can be divided broadly into three groups: explainability of programs, accessibility of the programming environment, and the efficiency of the programming process. The first idea is that programming can be used as a medium that facilitates understanding. I think that the mainstream view on that matter is that programs by themselves are difficult puzzles that require a lot of brainpower to be understood. And indeed, I think that this view might be deeply rooted in experiences of many programmers, deeply enough to be considered the norm. So in order to make programming understandable, we need to consider some principles that would help us explain why certain programs are more difficult to understand than others. Which takes us to the second idea, namely that it is easier to understand concrete things than to understand abstractions. In particular, it tends to be easier to understand concrete examples than abstract definitions. But instead of using abstract words, let me just give a concrete example of this. Consider the following definition in the Scheme programming language. Define multi-combinations from set A of length n. If n is equal to 0, return a list containing an empty list. Otherwise, compute multi-combinations from set A of length n-1 and then prepend each element from the set A to each combination from the result. This definition is not very long. I'd even dare to say it's fairly well written, but analyzing it seems to require a lot of mental effort. However, if we look at its usage example, we see almost immediately what's going on, and we would probably be able to correctly guess results for other values of input parameters, even without seeing any definition. I don't think that this statement is controversial, but I do feel that it receives much less attention from programming practitioners than it should. Examples can also help understand definitions. In particular, if a program is written in a functional or expression-oriented style, its execution can be modeled by substituting function invocations with their definitions, effectively presenting the evaluation process as an animation. But the question of concreteness and abstractness isn't bound only to definitions and examples. It's possible to write definitions in ways that are more abstract or more concrete. A while ago, someone posted the following snippet of code on social media. What I found striking about it is that you can show it to someone who isn't a programmer, and they will likely say, "Hey, I know what's going on in there." If I was to make this code more abstract without sacrificing too much clarity, I'd want to write it down in the following way. Unfortunately, our regrettable programming languages do not allow to work with such notations. But there's yet another face of concreteness versus abstractness in code, namely pattern matching, which is a technique of writing conditional code in a way that it resembles the data being processed. For example, instead of asking whether an object is a list of three elements whose first element is the symbol plus and then taking its second and third element, we could ask whether the object matches the specified pattern and simultaneously name some components from that pattern. But I can provide a more elaborate example of pattern matching. About a decade ago, I created a system for describing rules of chess-like board games. The system contained a language for describing allowed movements of specific figures. For example, the movement of a knight was described using the following rule. The rule consists of three parts. The first is a precondition, that is, a pattern that has to match somewhere on the board in order for the move to be allowed. A question mark means that a particular field can be in any state. An underscore means that the field is empty, and an empty box means that there's an opponent's figure on a particular field. The empty box /_ symbol means either an empty field or a field occupied by the opponent. The second part is a replacement, which describes situation on the board after the move is performed. The third part consists of a list of symmetries that could be applied to the pattern and replacement, so that repeating the same rule for every imaginable direction isn't necessary. In most implementations of the chess game that I've seen, the rule specifying the legal movement of a knight is usually described by means of indirection, that is, using numbers. A rule for expressing the legal moves of a bishop is even more interesting, and it looks like this. It contains a two-dimensional analogon of the Kleene star. A rule written in such a way is expanded from its smallest size, which is 2 by 2 in this case, to the size of the board. For example, on a 5 by 5 board, this rules pattern is transformed to the following set of patterns. Of course, the same thing could be written down using a more abstract but also more general and simple way, as in the following code. However, the fundamental difference between those two approaches is that the first one resembles the domain that it talks about, whereas the second doesn't resemble it at all. The pattern language that I developed made use of the fact that it's relatively easy to represent rectangular game board objects using Lisps as expressions. But there are many objects that do not lend themselves to such representation easily. Probably the most widespread of them are numbers, which are specific in the sense that they often have a geometric interpretation. On the other hand, they are usually represented using digits, and those digits by themselves rarely resemble any geometrical objects. For example, I think that most people would have a hard time guessing that the following points all lie on a unit circle by only looking at their digits. Another fairly common domain that isn't easily expressible by textual means are graphs. There are several different ways to represent graphs in code, such as neighbors lists. But none of those representations resembles the way we usually visualize graphs. The particular example of Grasp has actually been used as an illustration of the first prototype of Grasp. Unfortunately, the first prototype didn't have any way to add new representations in runtime, so the graph representation was hard-coded. This is a limitation that the currently developed version tries to overcome. But before we move on to the newer versions, let's summarize what we've said so far. Concretions are easier to understand than abstractions. Examples are a good way of providing insights about code. Program execution can be depicted as an animation. Defined terms can vary in their abstractness. Pattern matching is a way to make abstract code resemble concrete data. This suggests that Grasp should be able to represent data and patterns in a way that is closest to the domain of things being processed. Or, to put it differently, I would like Grasp to allow me to make my programs look exactly the way I want them to look like. Of course, when designing a programming tool, one has to take into account the existing ecosystems. In particular, if we look at the market share of mobile devices versus regular PCs in developing countries, we'll notice that mobile devices can be up to 4 times more popular, which is why it might make sense to create a programming environment that would support mobile devices well. But this is only one aspect. Another one is that touchscreens are a very interesting and largely unexplored medium, which creates a sense of directness that is unknown to users of regular PCs whose interactions with the things on the screen are intermediated by the canyon of keyboard and mouse. Of course, mouse and keyboard are still very effective input methods, and the regular desktop computers shouldn't be neglected. Ideally, an accessible programming environment should be available on as many platforms as possible. Lastly, I would like to tackle one other question before moving on to the demo. If we look at the 20 most popular programming languages, we'll notice that almost every single one of them is developed based on the idea that language design is about creating grammar that is imposed on unstructured text. The only language in the ranking that stands out from this crowd is Scratch, which usually isn't considered a serious or professional programming language. I think that there's a good reason for that. It is a frequent practice for programmers to design custom text-based configuration or data exchange languages, and the nice property of such formats is that they can be edited using the same tool that is used for editing their source code, and it's hard to imagine the Scratch code block editor being used in that role. What is perhaps a bit more puzzling is why there are no general-purpose structure editors that would operate directly on syntax trees. In either case, Grasp is an attempt to build such a thing. Historically, there's been a few attempts to develop Grasp. The most mature one was implemented in 2021, but due to a few fatal flaws in some of its design choices, it had to be re-implemented from scratch. However, since it is, at least at the moment of recording this video, the most feature-complete and usable version, I'm going to demonstrate it anyway before presenting the advancements in the latest prototype. This 2021 version only runs on Android. When you run the app, you see a blank screen. Swiping your finger on the screen will cause lines to be drawn. But when you tap the screen, they disappear. When you draw a box and do it in such a way that the gesture recognition algorithm recognizes that it is a box, it will turn into a pair of matching parentheses. You can use the left parentheses to move the box out of the document and the right parentheses to change its size. You can put boxes into other boxes, but this alone isn't very interesting. So you can remove boxes by quickly throwing them away from the screen. In addition to the box gesture, there's also underscore gesture, which opens an editor in which you can type text. You could also use speech recognition here if you have a proper keyboard installed on your system, but I'm not going to do that in this demo. You can type text into the editor, and this is the basic way of constructing programs. So in a sense, Grasp is just a more structural notation for S expressions known from Lisp-like languages. You can make a copy of an atom by double tapping on it. Likewise, you can make copies of compound expressions by double tapping on their left parent. Expressions can be evaluated by drawing a wedge symbol whose blade is above the expression that we want to evaluate. Grasp also lets you split screen by drawing horizontal and vertical lines, and the splits can be discarded by dragging them off the screen. The editor is complete in the sense that it lets its user open and save files, but there's a caveat. Newly created documents can only be stored in the so-called internal storage, and they cannot be exchanged with the rest of the system. The incorporation of boxes in the editor is not an accident. The point is that users should be able to extend editors' capabilities with magic boxes, that is, boxes whose content is drawn in a custom way and that can be interacted with in a custom way. At least that was the original plan until I realized that the presented prototype is a dead end because it's written in Java and the syntax of Java is not based on S expressions, so that at no point would I be able to use Grasp to develop itself. Also, it didn't support strings, comments, and dotted pairs, and adding support for those would be difficult with the chosen representation of documents. Because of that, I decided to rewrite it from scratch, this time in Kava, a scheme implementation that targets the JVM platform and can also be run on Android. The new prototype of Grasp can be run not only on Android, but also in the classical windowing environments using Java's AWT framework. Most surprisingly, perhaps, it is also possible to run it in the terminal. The Kava version of Grasp already supports most of the syntax of Scheme, including atoms, lists, dotted tails, strings, line comments, block comments, and expression comments. Grasp also supports quotations, which happen to be instances of magic boxes. You can observe that they are displayed using non-textual symbols. The syntactic components of Scheme that aren't yet supported by Grasp include vector syntax, syntax, quasi-syntax, and unsyntax syntax, and other syntactic extensions such as multidimensional arrays or uniform vectors. An important feature of the new implementation is full support for keyboard navigation and keyboard editing, with the goal of being at least as ergonomic as the classical text-based code editors. As in most other editors, Grasp uses a cursor for navigating and editing expressions. However, while in most text editors, cursors can usually be represented using two numbers, that is, a line number and a column number, in the case of a structural editor, things become a bit more difficult because a cursor must be represented by a path or a list of indices. In Grasp, this list should be read from right to left because this order is more natural when the cursors are represented using linked lists. So the last index represents the topmost expression in the document, and the first index is the index of the innermost expression inside of its parent. Also, when the indices are integer numbers, odd values typically represent actual elements, while even values represent spaces between those elements. The documents in Grasp are represented using const cells known from Lisp. Whitespace and comments are represented using weak key hash tables that are indexed by the identity of those const cells. The currently developed version of Grasp also supports the undo feature. Every operation on the document is intermediated by history, which gathers a list, or rather a tree of edits, where edit is an operation that can be inverted. The canonical examples of operations are insert and remove, which are mutually inverse, for adding and removing elements to and from a document, and move, which is its own inverse, which is used for moving expressions from one place in a document into another. Grasp also includes operations for splitting and merging atoms, resizing boxes, or commenting and uncommenting expressions. The interesting thing is that this sequence of edit operations can be perceived as an assembly program that operates on the document. Also, since the program is highly structured, there is an opportunity to look for patterns in the user's edits with respect to a particular document, and to extract new operations from those patterns, similarly to Excel's autofill feature. The most important feature of Grasp is its ability to present objects using a custom representation. Quotations were one example of that. Currently, Grasp provides another fairly rudimentary extension, namely buttons. There are some significant challenges for creating such an extension system. Currently, defining new extensions requires a lot of knowledge about the internals of the system. In particular, it should be possible to convert a magic box into a regular box, and this conversion should preserve all the information that is needed to reconstruct the current state of the magic box. Moreover, a care needs to be taken to make sure that all the edit operations are accurately represented in the document's history so that they can be undone. Lastly, the implementation of an extension is currently very low level. An enchanted element needs to provide a drawing function as well as functions to react to various touch events and key presses. And while it is not impossible to write extensions this way, I believe that there must exist a better way, which ideally would be about composing extensions from a set of building blocks. But I don't know yet exactly what such a language would look like. Currently, there are two very particular ideas that drive the development of Grasp. The first one is graph visualization and has already been mentioned at the beginning. The second is visual evaluation. I imagine that there could be a magic box containing buttons such as play, pause, skip forward, skip backwards, fast forward, and rewind, and which would make use of the substitution model of evaluation to present the execution of programs written in expression-oriented style as animations. Combined with custom representation of different types of data, this would create a very powerful combination of features to analyze behaviors of programs. Unfortunately, there still seems to be a long way before I can get there. My current milestone is to make Grasp powerful enough to be using it to further develop itself. But at the time of recording this video, I barely finished working on supporting file loading and saving, and the next positions on my to-do list were document scrolling and screen splitting. There's also a lot of bugs in the editing functions, and they will need to be taken care of systematically. Despite all that, I feel that Grasp is not very far from being usable, and there are some chances that I will manage to reach the milestone of self-editability before the live workshop actually goes live. Also, if you like the project, you can find its sources at github.com/panich/grasp.